the extreme value theorem is really all about finding maximums and minimums. That's what we're going to do here in Unit 3, Lesson 1. So I made a first part of this video or of this section explaining what critical values are, what critical points are. And so hopefully you know how to find those if you watched the first one, if you did this in class with me. Hopefully you'll know a critical value is one that makes a derivative equal to 0 or undefined. Okay, so we'll say that a lot. Once you know that, you can use the extreme value theorem, which I'll tell you what it is here in a moment, to find extreme values of functions and where they occur, which is just a fancy way of saying, hey, we're going to find the maximum, we're going to find the minimum. Now the nice part is if you're asked to use the extreme value theorem, and you wouldn't be asked in those words, you're given a continuous function on a closed interval. So let's think about this for a second. Let me get my cursor back. So a continuous function on a closed interval. So let's just say a to b. Okay. So can you connect a and b? Well, I guess that's pretty boring. If I just connect a and b with a straight line, do we get a maximum and a minimum? Well, yeah. What about if I make it a squiggly line or something like that? Does this graph have a maximum? One highest y value? Sure. Does it have a minimum? It does. So is there any way to connect these two dots with a continuous function where there's no highest y value? And of course that's not the case. The extreme value theorem says if you have a continuous function but on a closed interval as compared to an open interval, we'll do that in a second, that function on that interval is guaranteed to have one highest y value and one lowest y value. I mean, it could have a tie, like, so say sine of x on 0 to 4 pi, right, has a maximum of 1, which occurs at pi halves and 5 pi halves. Something like that. Okay. Anyway, so what would happen if you had not a closed interval? Well, even if that function's continuous, maybe like e to the x, does e to the x have a maximum or a minimum on, I guess, its entire range? No, because e to the x kind of grows forever. So what about if we chopped things off and went from maybe like -2 to e? Does e to the x have a maximum and a minimum on that interval, -2 to e? Well, yeah, right? The highest y value is on the right-hand side at e. The lowest y value is on the left-hand side, all the way at -2. Okay, people like step-by-step sort of things, so if that's you, here we go. So today, you should always be determining what to use, but if the extreme value theorem applies, you need to figure that out and you need to explain. We'll do that in a moment. The nice part about it is today, if the extreme value theorem does not apply, you don't do anything. In the future, if you can't use the extreme value theorem, then you need to find a maximum or a minimum. Another way, probably the first derivative test. That's much easier than the second derivative test. Wonder why that's in there like that. Oh well. So if the extreme value theorem does apply, we're going to find the first derivative because we want to find critical values. Critical values are ones that make the derivative equal to 0 or undefined. And then once we have the critical values, we substitute those along with the endpoints back into the original function. Because if we're looking for a maximum, we want the highest y value, and that's going to happen only at an endpoint or critical value. I should have step 5 here, which is write an answer. People sometimes forget to write an answer because they think, well, clearly 5 is bigger than 2, and they forget to write it. Anyways, so hopefully you know a whole bunch of parent functions or graphs, and you can use intuition, prior knowledge to guide you, but if we want to do well on the AP test, if you want to do well on my tests and quizzes, you actually have to use the calculus-based version, even if you've memorized a graph. So that's kind of nice. I guess you'd know where you're going, you just kind of have to prove things. Okay. So finding global extrema. And that's, again, a fancy way of saying, hey, find the absolute maximum, find the absolute minimum. So the first question is, does the extreme value theorem apply? Well, x squared minus 4x plus 3 is a polynomial. Polynomials are continuous and differentiable everywhere. That's a fun fact. And then we're given a closed interval. So that's the first thing I'm going to write down. So y equals x squared minus 4x plus 3 is continuous on the closed interval -2 to 5. Notice we don't have to write those words. We can just use notation for closed interval -2 to 5. And what I typically write is, so a maximum and minimum are guaranteed. I've found over the years students often forget the names of the theorems. And so you're always allowed to say what something means. And if we just practice that way, hey, this function is continuous on a closed interval, so we're guaranteed to find a maximum and a minimum. We don't have to remember that we're talking about the extreme value theorem. By the way, you could shorten that up and just say, can I get white here? We could just shorten that up and say, hey, y equals x squared minus 4x plus 3 is continuous on -2 to 5. So the extreme value theorem applies. That would be the other way to write stuff. Okay, so what are we going to do next? Well, the maximum or minimum can only occur at critical values and endpoints. We'll find y prime first. A critical value is where that derivative is equal to 0 or undefined. So where is 2x minus 4 equal to 0? At 2. So we're just going to say let y prime equals 0, 0 equals 2x minus 4, and x equals 2. Now you don't have to say y prime is always defined. But if you don't do that all the time, then when you're looking for a place where a derivative is undefined, or at least that's the thing to do next, you'll forget to do so. Anyways, so what do we do next? We make a table of values. And what are we going to put into that table of values? The critical value, x equals 2, and the endpoints -2 and 5. So hopefully you're not grabbing a calculator. You should be able to do these in your head. -2 squared is 4. -4 times -2 is positive 8. So 4 plus 8 is 12, plus 3 is 15. Pretty sure that's right. And then for x equals 2, that's going to be 2 squared is 4, minus 4 times 2 is 8, 4 minus 8 is -4, plus 3 is -1. And when x equals 5, 5 squared is 25, minus 20 is 5, plus 3 is 8. Let's see, did I match up? I try to do stuff ahead of time just so I'm ready. Cool. And so this is one of those weird things. You're expected to actually write an answer. We're supposed to find the maximum and the minimum, which is, wait, what's the maximum? Is the maximum, well, we know it's right here. So which one's the maximum, -2 or 15? Well, the maximum is 15, and it occurs at -2. Now, what about the intuition? Because back here I said, you know, if you use your intuition, prior knowledge, well, you should have been able to factor x squared minus 4x plus 3 to be x minus 3 and x minus 1 as those factors. So that's a parabola opening upwards, zeros at 1 and 3, has its minimum at x equals 2. And so, I don't know, we kind of should have been able to guess. So where are we going to get the highest y value? At 5 or at -2? Because we probably really didn't even have to consider 2. Although extreme value theorem says we do. And I guess what I'm thinking here, between 3 and 5, that's a change of 2. Between -2 and 1, that's a change of 3, so that parabola has more room to grow. Anyways, we do need to write an answer. And here's what I'm going to write. The global maximum of x squared minus 4x plus 3 on the closed interval -2 to 5. And you do need both, because sometimes you'll be given a derivative instead of a function. So we need to name the function we're finding the derivative of. And the reason it has a maximum is because we're talking about a closed interval. So we need to mention that interval. So on the closed interval -2 to 5. So the global maximum is 15. Notice I've said, hey, there's my y value. And that maximum occurs at x equals -2. That's the structure of what I've written. And then maybe I should repeat x squared minus 4x plus 3 in the closed interval again, but I think it's pretty obvious, so we don't. And the global minimum is -1, which occurs at x equals 2. I'll give you a second to write that down. Or heck, pause the video. So what about x cubed plus 3? Well, maybe can we think about that graph? So x cubed, minus 3. Minus 3. I know what x cubed looks like, so x cubed minus 3 looks like this. And I guess that's funny. That doesn't seem to have a maximum or a minimum, looking at those end behaviors. But don't forget, what we're really looking for is the extreme value theorem. Are we given a continuous function on a closed interval? No. So our answer is, and I wrote a little bit extra, but we don't have to. X cubed minus 3 is continuous, but no closed interval is given. So the extreme value theorem does not apply, and no maximum nor minimum are guaranteed. That's my answer for now. In the future, really, if we're looking for a maximum or minimum, we're going to go ahead and use the first derivative test, which my class doesn't know about yet. Okay. So how would we find absolute extreme values for x cubed minus 3 on the closed interval -3 to 5, right? Because we already knew x cubed minus 3 is continuous, and now we have a closed interval. So what am I going to say? I'm going to say x cubed minus 3 is continuous on the closed interval -3 to 5, so a maximum and minimum are guaranteed. You could have also finished off with, so the extreme value theorem applies. Where can that maximum and minimum occur? Critical values and endpoints. What's a critical value? A critical value makes a derivative equal to 0 or undefined. So we're just going to find y prime, 3x squared, and since all polynomials are continuous and differentiable everywhere, we know this derivative is never going to be undefined. Still going to write that. Y prime is always defined. That way I don't forget in the future. So once we set y prime, 3x squared, to 0, we get x equals 0. From there, hopefully you remember, we are just going to make a table of values with those endpoints, -3 and 5, along with the critical value 0. And again, don't grab a calculator. You should be able to do these in your head. -3 cubed is -27, minus 3 is -30. And don't forget, we already kind of imagined this graph. You should be expecting to find the maximum at 5 and the minimum at -3. Okay. 0 cubed is 0, minus 3 is -3. 5 cubed is 125, minus 3 is 122. Okay. Again, don't forget, we actually have to write out a result. Probably should have animated these. Oh well. And that result is, well, I worded it a little bit differently. For x cubed minus 3 on the closed interval -3 to 5, the absolute maximum is 122, and the absolute minimum is -30. Why didn't I mention the x values? I guess to prove a point that, did you actually notice we weren't asked for the x values? We were just asked for the absolute extreme values, which means just the y's. But we could have just as easily said, just the maximum is 122, something like which occurs at x equals 5, and the absolute minimum is -30, which occurs at x equals -3. You're always allowed to write things that are true on the AP test. Okay. I just recommend not writing extra if you don't have to, some of the time. Okay, so if we're going to find extreme values of 1 over x plus natural log of x on the closed interval 1/2 to 4, dang, I don't really know what that combined graph looks like. I can kind of figure it out, 1 over x isn't continuous everywhere, but it is continuous on 1/2 to 4. And then natural log of x is continuous on 1/2 to 4. And addition doesn't create any problems. So 1 over x plus natural log of x, we're just going to say is continuous on 1/2 to 4, even though we don't know what that graph looks like yet. And in fact, maybe the fun or annoying part of calculus is a lot of times we don't know. Anyways, so a maximum and minimum are guaranteed. And those maximums and minimums can only occur at critical values of endpoints. We need to find critical values. A critical value is where the derivative is equal to 0 or undefined. So derivative, pretty easy. The derivative of 1 over x is negative 1 over x squared. The derivative of natural log of x is 1 over x. And we're going to multiply the second term by x over x. So that way we have a common denominator. And it'll just be really easy to see where that derivative is equal to 0. So notice down here, negative 1 plus x over x squared is equal to 0 when the numerator is equal to 0, when x equals 1. And y prime is going to be undefined when that denominator x squared is equal to 0. So what numbers do we put? You hear my cat playing with a cat toy. What numbers do we put in our chart? Well, we ignore the 0. Because 0 is outside of 1/2 to 4. So we're just going to do 1/2, 1, and 4. And hopefully you realize, while we can do 1 over 1/2 and 1 over 1 and 1 over 4, we can actually do natural log of 1. We don't get much useful out of natural log of 1/2 or natural log of 4. So we're going to grab a calculator for those three values. Turns out, and almost all the time, let's say 90% of the time, if you're doing extreme value theorem, took me a minute, you're going to be using a calculator anyways. Well, you can see that at 1/2, 1 over x plus natural log of x is 1.306. At 1, we get 1, and at 4, 1.636294. So the maximum of 1 over x plus natural log of x, my L got deleted, on 1/2 to 4 is 1.636294, and the minimum is 1. Oh, it says and where they occur. I screwed that up. Which occurs at x equals 4, which occurs at x equals 1. All right. So a couple more. Let's think about what e to the negative x looks like on negative 1 to 1. And let's not use a really dark one. So e to the negative x looks like this. And so on negative 1 to 1, we should already know what to expect. We're not going to find any critical values, and we're just going to have a maximum at the left endpoint, negative 1, and a minimum at the right-hand endpoint. But e to the negative x is continuous everywhere, especially on negative 1 to 1, so the extreme value theorem applies, or a maximum and minimum are guaranteed. Y prime is negative e to the negative x, and then we already kind of knew this was coming. So if you know what e to the negative x looks like, you know what negative e to the negative x looks like, and that's never going to be equal to 0 is defined everywhere. So we get no critical values, which means when we make our table of values, all we have to do is substitute negative 1 into e to the negative x, and we get e, 2.71, I forget what it is, and 1 over e, a little bit more than a third. And again, that was predictable. So the maximum of e to the negative x on negative 1 to 1 is e, which occurs at negative 1, and the minimum is 1 over e, which occurs at 1. Now, this one actually might be a little bit interesting, because you might be thinking like earlier, well, 25 minus x squared, I don't know, I guess is continuous wherever, well, let's think about it. Wherever 25 minus x squared is, we want 25 minus x squared to be greater than or equal to 0, which is going to be, I mean, I don't really feel like doing the algebra because we'd have to test intervals, but hopefully you'd agree with, we can only put numbers into x and square them that are going to be between negative and 5 and 5. Because if we did something larger than 5 or smaller than negative 5, that x squared overpowers the 25. So even though we're not given explicitly a closed interval, in this case, the square root of 25 minus x squared kind of implies a closed interval, so the extreme value theorem does apply. So the square root of 25 minus x squared is continuous on negative 5 to 5, so a maximum and minimum are guaranteed. Where can that maximum or minimum occur? Critical values and endpoints. We actually have the endpoints. Now, instead of doing the derivative with the square root and the chain rule, we can kind of do a little bit of a trick here, square both sides, and we have a much easier derivative. So y squared is 25 minus x squared. 2y dy dx is negative 2x. dy dx is negative x over y. Now the cool part is we can just think through this. We want this derivative to be equal to 0 or undefined. And the derivative will be equal to 0 when x equals 0, when the numerator is equal to 0, and undefined when the denominator is equal to 0, or y is equal to 0. We do have to do a little bit of work to think about when y equals 0, but we kind of already did that. So we get negative 5 and positive 5. And the reason for that is what we were actually given was the top half of a circle with a radius 5 centered at 0, 0. And so at x equals 5x equals negative 5, this graph has vertical tangents, which is why that counts as no derivative at the endpoints. So anyways, we make a table of values. Negative 5 squared is 25. 25 minus 25 is 0. And we're actually going to get 0 for both endpoints. And you can see 25 minus 0 squared gives us 25. Square root of 25 is 5. So the maximum, and we don't have to say the interval because, well, the interval, I don't know, we created. I suppose we could. But the maximum of the square root of 25 minus x squared is 5, which occurs at 0. And the minimum is 0, which occurs at 5 and negative 5. So we'll end off with an easy example, and hopefully you can figure out why finding the extreme values of 2x squared minus 8x plus 9 is pretty easy. And that is, well, we know this is a parabola. There's no implied domain restriction. So no maximum, no minimum is guaranteed because we are not given a closed interval.